Hello students, welcome back to the microeconometrics course. Today we're going to start advanced panel data analysis. So let's start with fixed effects estimation. Fixed effects estimation is one of advanced panel data analysis, and we're going to start with the structure of the data that we're going to use for this panel data analysis. So basically the structure of our data is the following. So you have the dependent or the outcome variable y, and you also have control variables or covariates, and this is recorded in the factor x. And I is going to be the unit of analysis. This could be household, this could be firms, this could be districts, this could be province, and so on. And we also have the time periods. So we're looking at the same set of unit, individuals or households across periods. So for example, in this particular case, we have t equals to 1 until t equals to capital T. Now consider the case that n is large and t is a small or moderate. Now we're going to learn about the term balanced panel. So balanced panel is essentially you have the same set of individuals or the same set of firms across periods. So you have the same structure basically every year. However, when you're dealing with data later on, for example, you're using the Indonesian Family Life Survey or using panel data of macroeconomics data, you'll find that cases of unbalanced panel. So basically, the number of time periods is not going to be the same across individuals or across units. So for example, for one firm, you can observe it from 2004 until 2014. However, for other firms, they close down middle of the way, so you only observe their firm for 2004, between 2004 and then 2009. You don't see it for the rest of the year. So that's an example of an unbalanced panel. Again, this is due to attrition. And another thing is that, for example, if you want to keep the number of households or the number of units similar across periods, then what you want to do is that you want to replace the individuals who left out of the data with new individuals into the panel. So the main benefit of panel data is that with multiple years of data, we can control for unobserved characteristics that do not change or change slowly over time. And this is very, very useful for policy analysis and particular impact evaluation. At a minimum, statistical methods must recognize that the outcomes for a unit must be correlated over time. So if we're looking at wages of individuals across time, then we might think that my wage today is going to be correlated with my wage in the future, or my wage today is going to be correlated with my wage in the past period. Another example here is test scores. So for example, if you're looking at students' test score across years, say for example for math, then her math test score today is going to be correlated with her math test score in the previous year and of course later on in the year. Now this is quite contrast with pool cross sections. We have different sets of individuals in each period. So if there's some overlap, so for example, I'm randomly sampled to become a respondent in a national or large-scale survey this year, I may have a very small probability to be chosen again next year, probably a probability of 0.01. Now, in that particular case, then we usually ignore it. We're just going to assume that I'm just another, a random individual sample. I'm not going to be linked into my existing in the previous year's survey. So this is something that we discussed back in Econometrics 1, a very useful but quite straightforward method of first difference. But let's do a quick review of the first difference estimator because it's going to be very related to our discussions on fixed effects estimation. Okay, so we will start with the case of two periods, a very simple two-period model. We have t equals to 1 and 2. And we have, say, some observations on individuals or firms or districts or cities. Really depends on the data set and the analysis that you're after. So along with the observed data, of course, we observe the dependent or the outcome variable y. We're also going to observe, characteristics or control variables that are going to be useful in the estimation. And these are x1, x2 until xk. Now, along with this observed data, this is the data that we as researchers observe. We also draw unobserved factors. And so what are the unobserved factors? That's something that you have to think quite hard given the data set that you're looking. So for example, if you're looking at individual data set on wages, then you should think what are unobserved factors that affect the wage but may not be observed in our data set. Similarly, if you're looking at, say, for example, a panel data of student test score, you can observe their demographic characteristics. You can observe their family's academic background, their family's labor market background, and so on. But there are also unobserved variables. So, for example, motivation of each student could be different. The motivations of parents could also be different, and this is not something that we can see in the data. Now let's break it down into a finer components. So there are two components or two categories. The first one is a component that doesn't necessarily change over time, and we're gonna write this as AI. So this is called an unobserved effect or unobserved heterogeneity. So this is referred to as the unobserved heterogeneity because, again, my motivation could be quite different to the motivation of the next guy sitting beside me, and it's going to be different to the other individuals as well. So this is quite complex. We can't really see it, so it's very difficult to quantify, but there are examples that are useful. So for example, it's my motivation in my job, the way that I make my network, and the way that I maintain my network, for example. These are important things that could be quite useful in maintaining your job, and then that would eventually affect your wages. So this is something that we need to think about when we're doing analysis, is try to understand what are the unobservable that could be correlated with the outcome of interest, and then at the same time, what are the unobservable that also correlate with the main explanatory variable that we're looking at. This is a discussion on omitted variable bias that we discussed in earlier lecture. So this unobserved heterogeneity varies by individual, but it doesn't really vary over time. So at the individual level, we can think of AI as ability, as motivation, as grit, for example, something innate and not subject to change. Generally, AI is going to contain unobserved attributes. Now, the second component is going to be unobservable that change across time within that individual. And so these are sometimes called shocks. Others call this idiosyncratic errors. So this shock is very, very specific to unit I, but vary over time. And the unobservable, the shocks actually affect the outcome of interest as well. So given this particular slide, we notice that not only factors that we observe affect outcomes of interest or the outcome variable, but the unobserved variables also affect the outcome variables. Now, trying to better understand what are these unobserved factors are also going to be very important in the estimation of panel data and in estimation of econometrics model in general. Okay, so let's go and dig into the equation. So here you have the outcome variable y of it. You also have a dummy variable which is equal to 1 if it's in the second period. Remember, we only have 2 periods here. And then you have the explanatory variable. I'm just going to use one explanatory variable for simplicity, and then you can extend it to multiple explanatory variable in a straightforward manner. Now we also have this composite error term, and this composite error term can be broken down into two components as we've discussed. The first one is going to be the unobserved heterogeneity, and the second one is going to be the shocks. So again, this is something that you have to be very, very mindful. Try to imagine, try to think, try to kind of like understand what are the factors that we do not observe that affect y, and at the same time it could be correlated with the explanatory variable of interest. Okay, so there are some assumptions conditional on regressors here. I do not explicitly write it, but let's assume that it's conditional on the regressor, then the expected shock is going to be 0, and then the expected shock across individuals are not going to be correlated. So for example, on average, the shocks that affect me is not going to affect the other individual as well. Another one is that there is no correlation between the unobserved heterogeneity and the shock. So we can think of the fact that the shock is literally external shocks, and then this is an exogenous shock. Something that we can control, and it's not correlated with our behavior, it's not correlated with our characteristics. And also, as with any other regression, we're also going to assume that the shocks are not going to be correlated with the variable of interest, in this case is x. Now, we're not going to make any assumption on the correlation between the unobserved heterogeneity A and the explanatory variable of interest, in this case x. Now, the first question is, how should we estimate the slope beta 1 and of course beta 0 delta 0 along with it? Well, one possibility is just to use pool OLS. So you have a panel data and treat it as a pooled OLS. Can you do that? Yes, of course. However, there are going to be disadvantages that we're going to discuss. Now, let's do it and then assume that we're going to use the panel data and estimate this as a pooled OLS. So effectively, let's define the composite error. Again, this is comprised of the unobserved heterogeneity and the shocks for the two periods that we have in the data. Now we're going to write the equation, and then the issue is that by kind of like not decomposing the error, what we're going to have is that correlated standard errors, and then there is also the issue that the unobserved heterogeneity AI in this composite error term is going to be correlated with the explanatory variable of interest. And then we discussed this before, correlation between factors that we do not observe and the explanatory variable of interest is going to make the estimated beta 1 hat is going to be biased. Now, in this case, if the bias is introduced by this heterogeneity across individuals, then we're going to get what's called heterogeneity bias. Okay. Now, to remove heterogeneity bias in pooled OLS, now this is what we can do. Now, write time periods in reverse order. So instead of writing the first period and then the second period, we're going to do it the opposite. So we're going to write the second period first. So yi2 is going to be equal to beta 0 and delta 0. Again, delta 0 is the coefficient for the time dummy. So if it's in the period 2, the dummy equals to 1. So delta 0 times 1 is going to be delta 0. And then you have beta 1, the value of x's in the second period, the unobserved heterogeneity, and the shock in the second period. And of course, we have the first period. This is basically the same structure. Again, in the first period, the time dummy variable is equal to 0. So delta 0 times 0 is going to be 0. So you don't have this beta 0 here, delta 0 here. Now, given that you have this reverse structure, what you can do is that you subtract the time period 1 from time period 2. So what you get is that you have a difference in the outcome variable, and then the difference in the explanatory variable, and then change in the shocks, the unobservable shocks. Now, this is something that is quite useful. Why? Because you can now notice that the unobserved heterogeneity A is eliminated from the regression. Now, we have to be very careful that this method is actually very useful in 2-period panel data, and this method is going to be undesirable if we have more than 2 periods. So we must account for serial correlation because the first difference equation is no longer just a single cross-section. So again, you have a 2-period panel data and you're doing a first difference analysis, then your data basically shrinks into a cross-section. Now, if you have, say, for example, 3-period panel data and you apply the first difference method, then what you get is that you have 2 years of cross-sections basically. Now, and that's going to be quite difficult, and particular in the estimation of the standard errors, because the standard errors are actually going to be correlated across time. Now, that's basically the idea of the first difference estimator. Again, we want to do the first difference estimator because the heterogeneity bias. So the unobserved heterogeneity can easily be correlated with the variable of interest x, and so one of the methods that we can do to actually eliminate the unobserved heterogeneity from the equation is the first difference estimator. Now, we're going to use the same logic, we're going to use the same concept to explain the within estimator. So within estimator is it's an estimator for panel data analysis, and this is going to take advantage of the fact that we have unobserved heterogeneity that don't really change over time. And so what we can do is that we can create kind of like a time mean for each variable, and then for each years of observation we're going to time demean it. Let's take a look more closely. So differencing is just one method of eliminating AI. Again, which itself is sometimes called a fixed effect. For the it's fixed for the unit of observation. So for example, it means fixed effect by the fact that the effect that I have on myself is going to be different to the effect that someone else has on the outcome variable of interest. Now, alternatively, we can use the fixed effects or the within transformation to remove the within I time average. Now, we'll take a look at this more closely. Now, in this simple model with only one explanatory variable x, again, you can easily extend it to multiple variable. And then what you can do is that, suppose that you observe this data for multiple years. So for example, for 5 or for 6, let's take 10. And then average this equation across t. So you have average y across the 10 periods. You have average x across the 10 periods. Again, this unobserved heterogeneity doesn't really change because by definition this is something that do not change over time and specific to that individual I. And we also have the average shock across here. Again, this average shock is something that we write in the specification, but it's not something that we necessarily see in the data set. Okay, so y bar, x bar, and u bar is just basically, again, is the mean of the outcome variable y, it's the mean of the x across period. So this is called the time average. Now, with the same idea as the first difference estimator, what we're going to do is that we're going to subtract the time average equation. This is called sometimes the between equation from the other time periods. So for each time period, so for example, the first period, we're going to subtract it with the time average. For the second period, we're also going to subtract it with the time average, and so on and so on. Again, why do we want to do this? In the basic equation, we have this unobserved heterogeneity. And again, if this unobserved heterogeneity is correlated with the variable of interest, and at the same time, by definition, AI is also affecting the outcome variable, then the consequences is that our beta estimation of beta 1 hat is going to be biased, or in other cases our expected value of the estimate is not going to be consistent, and that's going to be quite detrimental into the estimation of impact, for example. Okay, so just going back to the time demeaning equation. So what we have here is basically quite similar with the first difference equation, and this equation is now free of the unobserved heterogeneity A. Now we view this time demeaned or within equation as an estimating equation. Now, as with the first difference, we can interpret beta 1 in the levels equation like the following. So suppose that the left hand side variable is the log of wage, and then x is the years of schooling, then we can interpret beta as the return to education. So another year in school is correlated or is has a relationship with a higher wage by, say, for example, 6 or 7%. It really depends on the value of beta 1. Now we can use the pool OLS on the deviations from time averages to estimate beta 1. I'm going to call this the fixed effects estimator or the within estimator. Now again, as I said previously, for the sake of discussion, I showed you a very simple two-variable panel data model. And now what we can do is that we can add more explanatory variables into the equation. So for example, in this particular case, not only that I have x1, but I also have x2 and so on until xk. So basically here, if you're running a regression on wages, then for example, you wanna add the characteristics of the individuals, say for example, their age, and then their years of schooling, their gender, their province of living, and so on and so forth. However, there's a caveat, as you will see, that for example, gender doesn't really change over time, and then the years of schooling for those who do not go to school anymore is also going to be unchanged. So if variables do not change over time, then it's going to be eliminated in this fixed effects regression. Why? Because again, for each variable, you're taking the time average, and so if the variable doesn't really change, then the value of the variable minus the time average is going to be 0. So again, you have to be very mindful on the variables that you choose for fixed effects estimation. In general, it has to be variables that the values vary over time. Okay. Now let's use the time demeaning on each variable. So we have y minus y bar, we have beta 1 multiplied by x1 minus x bar, and so on and so forth. And what we can do is that you can just do pool OLS regression using the time demean variables. Okay, so let's take a look at the assumptions for the fixed effect. So basically, beta j's are going to be the parameters that we're going to estimate, and AI is the unobserved effect. So this is how important the unobserved effect or the unobserved heterogeneity is that it's included in the assumption of the fixed effect. Again, as with any estimation in econometrics, we want to have a random sample from the cross-section. So basically, before the data was collected for the first period, we want to make sure that the cross-section that we choose is going to be random, a random sample from the population. And we're going to follow that over time. And each explanatory variable changes over time. And no perfect linear relationship exists among the explanatory variable. So let's take the first part of this assumption. So this is something that I've mentioned before. If you want to use the fixed effects estimation, you cannot use variables that do not change over time, such as gender and then years of schooling if you finish schooling. And And the second part of the assumption is that there is no multicollinearity, and this is something that we can definitely test to see. Okay. Now for the fourth assumption is that for each t, the expected value of the idiosyncratic error given the explanatory variable or conditional on the explanatory variable in all time periods and the unobserved effect is going to be 0. What it means is that the unobserved shock is going to be random. Okay, it's not going to be correlated with the explanatory variable. It's not going to be correlated with the unobserved heterogeneity. It's purely random. Okay. The fifth assumption is that the variance conditional on the unobserved heterogeneity and then the variable of interest or the covariate is going to be constant. So basically this is kind of like the homoscedasticity assumption. Now again, dealing with this panel data where we observe outcomes across periods, then it's going to be quite difficult to assume that the variance is going to be constant across year, or for example, it's going to be constants within individuals. So we've seen in the DID lecture, what we can do is that we can use the cluster robust standard error within the unit of analysis. It could be the individual, it could be the firms, depending on the data that we're looking at. And then the sixth assumption is that for all t not equal to s, the idiosyncratic errors are going to be uncorrelated. So again, this is conditional on explanatory variables. So what it means is that there is not going to be serial correlation of the shocks across period. Okay, and the seventh assumption is that conditional on x and the unobserved heterogeneity A, the shock are going to be independently and identically distributed as normal. We want this assumption so that we can generate estimates assuming normal distribution. Okay. So let's discuss some properties of the fixed effect estimator. So the fixed effect model is going to allow a degree of correlation between AI and the explanatory variables in any time period. Now, the exogeneity assumption for unbiasedness is the following. The idiosyncratic error should be uncorrelated with each explanatory variable across all time periods. And the idiosyncratic errors must be homoscedastic and serially uncorrelated across t. Again, if this is something that is challenging and we feel that it's a very difficult assumption to fulfill, then what we can do is that we can relax the estimation of the standard error, say for example using the robust standard error or the cluster robust standard error to take into account the nature of the variance of the unobservables. Okay, so just a quick review of LSDV or the least square dummy variable. Again, this is very, very similar to the idea of fixed effect. This is another way that we can actually estimate fixed effect. However, as we will see, this is going to be costly. We'll see what I mean by costly here. So there is another way to compute beta 1 hat in this fixed effect estimation. So we're going to keep the original data, y and then x, and then run regression of y on n dummy variable. So basically, again, for each individual, we're going to observe, we're going to have unobserved data, and so this unobserved data or this unobserved heterogeneity is basically the fixed effect. So what we were going to do is that we're just going to include dummy for each individual in the data set, if we have an individual level data set, or for example, if we have a firm level data set, then what we're going to do is that we're going to include firm fixed effect. So this is called the dummy variable regression. So as you can see here, I'm going to regress y on x1 until xk, and at the same time I'm going to include dummy variables where n is equal to 1 if it's the first individual, n2 is going to be equal to 1 if it's the second individual, and n is going to be equal to 1 if it's the nth individual. Now, Again, this is costly. Why? Because we're going to have a very large n, and in this case, we're going to lose a lot of degrees of freedom. Now, Stata is going to report a constant or intercept with fixed effect estimation, but beta 0 gets eliminated by the fixed effect transformation. So what is the estimated intercept? Well, it is just the average of the n coefficients of the dummy variables. But again, we don't really take a look into, we're not really concerned about the constant. So this is rarely of interest. Okay, so far we've discussed two methods for estimation of panel data set. The first one is going to be the fixed effect. The second one is going to be the first difference. And now the first question that we want to answer is that should we choose first fixed effect or should we choose the first difference estimator? But basically, if we just have a 2-period panel data, t equals to 1, 2, then the fixed effects and the first difference is actually identical. So either way, you're going to get the same result. Now, the first difference is going to be quite straightforward because it's going to be a cross-sectional estimation. So if you're dealing with very, very large data set, then first difference could be more straightforward. Now remember that the first differencing can also be used if t is larger than 2. So for example, for a 3-period panel data, for a 4-period panel data, you can always use this first differencing. But again, there are going to be issues. One is going to be the correlated standard errors across time. And so in this particular case, then the fixed effects is actually going to be more efficient if the classical assumptions hold. So efficient here means that it's going to produce the lowest standard error. Okay, so just to wrap up, we reviewed first differencing method. We also reviewed the fixed effect method. These methods are actually very identical for 2-period panel data. It's actually identical for 2-period panel data. And for t more than 2 periods, so for example, 3-period panel data, 5-period panel data, 10-period panel data, then the fixed effect estimation is going to produce a more efficient estimator. Okay. Now let's take a look into the second method, the random effects estimation. So again, we're going to begin with the same unobserved effect model. This is something that we've seen in the discussion of the first differencing method and the fixed effects method. So here we basically have the outcome variable y. We also have the explanatory variable of interest, x1 until xk. We're also going to get unobserved effect or unobserved heterogeneity and shocks. Okay, so that we assume that AI is uncorrelated with each explanatory variable in all time periods. Okay, so this is very strong. We're going to assume that this unobserved heterogeneity is going to be uncorrelated with the explanatory variable in all time period. Again, this is an example of a very strong assumption. We'll see in cases where we can actually use this assumption. Okay. Now, if it really is uncorrelated, then this A is going to provide information. And so eliminating AI is going to result in inefficient estimators. Okay. Now the model above is going to become a random effect model when we assume that the unobserved effect A is uncorrelated with each explanatory variable of interest. Okay. So again, this is going to be a random effect model relies on the assumption that the unobserved effect is uncorrelated with the explanatory variable of interest. So for example, if this is education and this is motivation, then this assumption says that whether you're motivated. So motivation is not correlated with the years of schooling or the years of education. So this is something that we're going to assume if we're gonna. So if we want to use random effect model, this is something that we're going to assume. Another example, say for example, if you have a firm panel data, then one of the unobserved variable or one observed heterogeneity is firm's culture. And for example, the variable of interest is going to be the output or the productivity. So the random effect is going to assume that the firm culture is not going to be correlated with firm's productivity. Again, this is something that's going to be quite difficult to defend, given that this is a very strong assumption. And so here, very early on in the discussion of random effect, you can already identify how the assumption of random effect is going to be quite different with the assumption of the fixed effect model. So in the fixed effect model, we actually allow correlation between the unobserved heterogeneity and the explanatory variable of interest. In the random effect, is less forgiving. It mentions that no, there should be no correlation between the unobserved heterogeneity and the variable of interest. Okay, so if we assume that the unobserved heterogeneity is independent to the explanatory variables of interest, we can treat the data as a single cross-section. Well, not necessarily. There are going to be disadvantages. Again, you have a very rich panel data set, and usually it's difficult to establish a panel data because you have to follow the same set of unit across periods. It's also going to be quite expensive in the data collection process. Now, so that's one disadvantage. We're not taking full advantage of the rich data set. And again, outcomes are going to be correlated across time. And so this is something that we may not be able to accommodate in the single cross-section. So alternatively, we can use the pool OLS procedure. So again, you have a panel data, but you're going to treat it as pool cross-section. And then in the estimation, what you want to do is that you want to include time dummies. You want to include these time dummies or time fixed effects to control for factors that do not change across units within that time period. Okay. And so suppose that, again, the composite error term is going to be comprised of the unobserved heterogeneity and the shocks. And you have this following regression. So if you do a pool cross-section, then you're going to assume that this is going to be the equation. You're going to assume composite error term. Now, the composite error term is going to be correlated across time. Due to what? Due to the fact that the composite error term has this unobserved heterogeneity. So in every period, you're going to have that unobserved effect. And so basically, the error term today is going to be correlated with the error term in the previous period. Now, the positive serial correlation can be substantial. And so the estimate of the standard error from the pool OLS is going to be incorrect. And so basically, if the unobserved effect has positive correlation across time, then your standard error is actually going to be underestimated. What it means is that the true standard error could be higher than the one that you estimate. And what's the consequence? Well, the consequence is that you're going to face a larger probability of type 1 error. Okay, so let's go through the assumptions of the random effect. Again, there is no perfect linear relationship or multicollinearity among the explanatory variable of interest. The second assumption is that in addition to the fourth fixed effects assumption, the expected value of the unobserved effect given all explanatory variable is just a constant. Okay. And then assumption random effect number 3 is that in addition to the fifth fixed effects assumption, the variance of AI given all explanatory variables is going to be constant. Okay, so again, this is in addition to the fixed effects assumption number 5 on homoscedasticity. So recall that the variance of the shocks conditional on the unobserved heterogeneity and the explanatory variable of interest is going to be a constant. That's the fixed effect assumption number 5. And here we're just going to add another layer, is that conditional on explanatory variable, the variance of the unobserved heterogeneity is going to be a constant. So here we can use what's called the GLS, or the generalized least square, to tackle the serial correlation problem. So if you notice, this is actually a topic that you discuss in Econometrics 1. And this in Econometrics 1, and particularly in the discussion of serial correlation in time series data, you acknowledge that the observation today or the unobserved factor today could be correlated with the unobserved effect in the previous periods and so on. So there is that correlation across period, and one of the things that we can do is to use a generalized least square. So basically this is a modification of the ordinary least square to accommodate the issue that we have in the composite error term. And so here we're going to do a transformation. We call this the GLS transformation. And so we want to do this GLS transformation in such a way that we're going to get more efficient estimation. And so here, theta is going to be our parameter of interest. Again, theta is something that we have in the population. Theta is something that we're not going to be able to observe, but this may be something that we can estimate. We'll discuss that later. So the sigma square u is going to be the variance of the shocks, and then sigma square a is going to be the variance of the unobserved heterogeneity. Okay, and so we're going to use this theta into the equation. So just briefly take a look at this estimating equation. So you have yit minus theta y bar. Y bar is going to be the average across period, and then beta 0 1 minus theta, and then you have beta 1 x1 minus theta x bar. Again, x bar 1 is going to be the average value of x1 across time, the average, and so on. So we'll see this transformation later in Stata, but what we can do is now is to estimate theta. Again, theta is something that we don't see because this is something in the population, but we still need a consistent estimator on the variance of the shocks and the variance of the unobserved heterogeneity. And so what we can do is that we can use the pool OLS and the fixed effects residuals to actually get this two estimates. Now after that, Stata is going to use those estimates to compute or to estimate some versions of theta hat. Okay. Now the feasible GLS estimator that uses the theta hat in place of theta is going to be called a random effects estimator. Okay. Now let's take a look at the estimating equation once more. Now take a look at theta and assume different value of theta. What would happen, say for example, if theta or theta hat for the feasible GLS, but let's just take it on the theoretical parameter theta first. If theta is 0, then you can see is that the estimating equation shrinks into a pool OLS estimation. What happens if theta is actually equal to 1? Then the estimating equation is actually a fixed effect estimation. Okay. Now, if in limit, if we have a very long data set and theta hat is close to 1, then the random effect and the fixed effects estimates are similar. Now, it doesn't mean that we can use either the fixed effect or the random effect. We really have to go back to the assumptions. The assumptions on whether the unobserved effect A is correlated with the explanatory variable of interest X or not. If it's not correlated, then we're going to be able to use the random effect estimation. However, if the unobserved heterogeneity A and the explanatory variable X is actually correlated, then we should use the fixed effect model. Okay, now this is a very large discussion in itself, but I'm going to make it relatively brief. So we discussed why we want to use fixed effect as opposed to first difference and the other way around. It really depends on the structure of the data. But now, given that we have, say, some panel data, like more than 2-period panel data, whether we should use the fixed effect or the random effect model. Well, again, when is the fixed effects estimator desirable? Well, again, the fixed effect is going to allow arbitrary correlation between the unobserved heterogeneity or the unobserved effect and the explanatory variable of interest. On the other hand, when is the random estimator desirable? Well, random effect allows analysis of time invariant variables such as gender or the years of schooling and so on and so on. And so basically, if our interest is in a time varying X, so for example, if we want to estimate whether or not the effect of X, which is varying over time, can we ever use random effect? The answer is yes. However, you have to fulfill one of the main assumptions, which is no correlation between the variable of interest and the unobserved heterogeneity A. Okay. Now, given your read of the literature and given your discussions perhaps with your colleagues in the past, you may encounter the Hausman test. So basically, the Hausman tests tell you that the null hypothesis that the random effect is a more efficient estimator in this case. Now, if the test fails to reject the null, then the random effect and the fixed effect are sufficiently close to each other. And if the test rejects the null, then the fixed effects estimates are used. Now, a shortcoming of this test is that it requires the random effect estimator to be efficient. However, in a panel data set, it's very difficult to get the random effect estimator to be efficient. Why? Well, again, the composite error term is inherently serially correlated, and so what we can do is that we need to cluster the robust standard error estimator before we get that efficient random effect estimator. And so, as opposed to just using the Hausman test, we actually need to start to use the robust Hausman test. This robust Hausman test actually take into account the fact that the composite error terms are correlated across time. Now, I just want to be very, very blunt here. The choice of using fixed effect or random effect cannot just be based on whether or not, or what the robust Hausman or the Hausman test tells you. It really has to be based on the design of the estimation. And so what we mean by design is that whether or not that unobserved heterogeneity is correlated or not with, it's whether the unobserved heterogeneity is correlated with the explanatory variable of interest. If so, then fixed effect is going to be more desirable, but then if it's not correlated, the random effect is going to produce a more efficient estimate. So that's something that we have to take into account. So we just can't go and, oh, let's see what the Hausman test tells us and we'll choose whatever estimate that you think the best. That's not the case. We have to start from the design. Okay. So some decides whether to use fixed effect and random effect based on whether or not this unobserved heterogeneity are viewed as parameters or random variables. Again, this AI unobserved heterogeneity is not a parameter of the model. This is something that we do not observe. And so basically, again, the idea of choosing between fixed effect or random effect is not based on whether or not AI is a parameter or not, or as random variables. It's actually, we have to look at what is the unobserved behavior that could be reflected in this AI, and that's something that we need to take into account into the design. So the unobserved variable, or AI, is the key debate on whether or not we're going to assume AI is uncorrelated with all the explanatory variables or the explanatory variable of interest. If you argue that it's not correlated, but for example your counterpart or your colleague finds that, oh hey, I can think of a example why this unobserved heterogeneity is actually correlated with X, then your assumption may fail. So you have to be very, very mindful and thinking about whether or not this is correlated or not. In most cases, if we're looking at secondary data or if we're looking at observational data, then it's quite difficult to assume that the unobserved heterogeneity is going to be correlated with the explanatory variable of interest. However, if you're dealing with cases like field experiment or lab experiment, and then a randomized controlled trial, then your choice or your explanatory variable is not going to be correlated with your motivation. Why? Because X is by definition, or the policy variable by definition is randomized in the experiment. Okay, so we cannot treat our sample. So in another case, we cannot treat our sample as random sample. So for example, if you're looking at fixed effect at the province level, or you're looking at a panel data at the province level, or you're looking at a panel data at the country level or at the district level, our sample is not a random sample. And so in this particular case, we need to use the fixed effects. Okay. So in general, fixed effect is more convincing than random effect for analysis using aggregated data. Okay, so be very mindful when you're using aggregated data for analysis, and fixed effect is going to be more convincing. Okay, and so I'm gonna switch gear and head to Stata. And I'm going to provide you with very brief background on panel data analysis using Stata. Again, this is going to be very simplistic, and it's going to be quite different with the actual panel data that you're going to be facing, because in reality, what you need to do is you need to collect the data, you need to clean the data, make assumptions on the way that you clean the data, and so on until you have that regression data set. Here we're just going to use a data set that is readily available, and then we're going to do analysis based on that. Okay, so let's switch gear to Stata, and what we're going to do today is that we're going to use a data set from Kammerer and Trivedi's textbook on microeconometrics using Stata. And so the data set that we're going to use today is going to be called MUS08 PSID extract. So this is from panel survey of income dynamics, or the PSID, and this provides you with the wage data from 1976 to 1982. So this is from a data set from Baltagi and Kanti-Akom in 1990. Okay, well, the first thing that you want to do is that in every panel data analysis, you want to declare to Stata the cross-section variable, which is the individual ID, and the time variable. Okay, and here Stata is going to identify whether your panel data is strongly balanced, as in this case, or is actually not balanced. Now, the next thing that we can do is we're going to describe the data. Here we have years of experience, weeks of work, occupation, the type of industry, residence, SMSA. This is the standard metropolitan statistical area, marital status, female or male, and then if the wage is set by union contract, and then years of education, This is an indicator of race, 1 if it's equal to 1 if you're black, log of wage, and then the time dummy, okay, or the time fixed effect. This is something that okay, so let's we can view the organization of the data set. For example, we can list ID and then the time variable, years of working experience, and then weeks work, and so on. So I'm just going to look at observation 1 until 3. Okay, so this is basically the structure of the observation. For individual with ID 1, this is the observation in year 1, year 2, and then year 3. Okay, now you should know whether or not this panel data is in the wide format or in the long format. So if you're in the wide format, then the observation by year is actually organized by columns. If it's long format, then your data is actually organized by rows. And so in this particular case, let's take a look. Well, for individual 1, we have observation of year 1, year 2, year 3, year 4, and year 7, and it's organized by rows. In this particular case, you have a long data set, or the long format. Okay. Now, we can do a summary statistic, but instead of using the sum, we're going to use the XT sum of the cross-section and the time variable log wage, and then education, experience, square of experience, and then the weeks work, south, and then we can also use the time dummy if you want. Say, I'm just going to include a couple, but ideally you want to include them all. Okay, and so we have here is the overall mean and standard deviation, but we also want to know the variation between individuals and then the variation within individual. Now, as you can see, the ID variable here doesn't really change the same individual, and in this particular case there is no within variance. Okay, but there are between variance. But again, this is ID variable, it's not really that meaningful. Okay. Now, for example, this T variable, it doesn't vary across individuals because we all observe a period 1 until period 7, but it actually varies within individuals because we observe individual at period 1, 2, 3, and 4. Again, this is not a meaningful variable, but I just want to show you the difference between the within variance and then the between variance. Okay. Okay. So we can do also tabulation of a variable. So for example, in this particular case is the indicator on whether or not you're in the south or not. Here we can also see the overall variance and then the between as well as the within. And it's also interesting that Stata provide us with the transition probabilities for a particular variable. So in this particular case, we want to see whether or not individuals actually move between areas. So for example, in this particular matrix, 99.68% of individuals stay in the non-south area, and 99% of individuals stay in the south area. However, among individuals who stay in the south area, 0.77 actually move to non-south area, and within those in the non-south area, 0.32% actually went into the south area. So this transition probability is actually very useful in looking at whether or not the south area is a variable that changes over time or is actually a variable that do not change over time. If the value here is 100, 100, 0, and 0, it means that the variable south is variable that do not change over time, and that's something that we cannot include in the fixed effect estimation. Okay, so I'm just going to provide you with just a very simple graph of log wage and experience. So in this particular data set, we actually want to know the relationship between experience and log of wage. Okay. And so we know that the experience and log of wage has a quadratic relationship, so we want to include also the Q-fit. and then just want to use the lowest, log wage, and then experience. Okay. Okay, so here I'm looking at the regression fit of the years of full-time working experience and the log of wage. We know that is not a linear relationship; it's a quadratic relationship. So basically, as you gain experience early on, you're gonna get a higher wage until that point where additional years of experience you get less productive, and then you get a lower wage. Okay, this is called the overall scatter plot. What you can do is also you can do a within scatter plot. So since I'm going to do some modification to the data set, I'm going to do preserve and then xt data fixed effect. Okay, and so in this particular case, what we have here is that here we have ID1. This is individual 1 for all time period. What we're going to do here is we're going to observe the average for the explanatory variables. Okay, and so I'm going to do basically just the same graph. So I'm going to copy paste it here and then do the graph again. So in this particular case, as we can see, while the relationship is relatively near, but this is to our eyes, we're going to see whether the relationship is indeed linear or is actually non-linear. Okay. Okay, and then let's do restore to get our initial data set back. And then I mentioned to you several times during the lecture that the unobserved variables is actually autocorrelated. So what we can do is that we can sort the ID, the cross-section variable, and the time variable, and then we want to see whether or not the log wage is correlated with the lag one of log wage. So as you can see here, the correlation is actually very, very high. It's 0.9189, and so in this particular case, there is an issue of serial correlation, and this is something that we have to pay attention to. Okay, so this is the correlation between the wage. Now, what we're gonna do is that we want to know whether or not the residuals are also correlated across time. And so I created. So I'm just going to do a quick regression. So log of wage, and then I'm going to regress it on experience and then the square of experience. So this is the way I write it, or you can actually just use experience and then experience square. It doesn't really matter, it's the same. And then I'm going to use cluster ID. Okay, and I'm going to predict the residuals, and I'm going to name the predicted residuals as U hat. Okay, now I created a loop, and so I'm just going to run the loop, and the loop tells us that the correlation at lag 1 is 0.884 and the correlation at lag 6 is 0.729, which is still high. So it means that the residuals are also correlated, and so if the residuals are correlated, then we may violate one of the assumptions. Okay, so I'm going to run the first estimation, which is the OLS estimation. So basically this is just a linear regression. So as you can see here, the estimated coefficient for experience and the estimated coefficient for the square of experience are all significant at the 1% level, even lower at the 0.1% level. Now, the next thing that what I'm going to do is just do some comparison on the fixed effect estimation. So in the fixed effect estimation, one thing that I should note to you is that I do not include variables that doesn't really change over time, that do not change over time. For example, in the OLS, I have an indicator of gender, union, SMSA, and so on. In this particular case, I do not include the indicator of gender because it really doesn't change over time. However, I do include union, SMSA. Why? Because these variables actually change over time. Now, as you can see, there is a stark difference between the estimate from the OLS and the estimate from the fixed effect estimation. And in particular, the estimate from the OLS is actually way lower than the estimate from for the fixed effect. So if we recall, the estimate from the OLS is 0.03 and the estimate from the fixed effect is 0.11. Very large difference. Okay. Now let's see another example, which is the random effect assumption. So recall that for a random effect estimation, the first thing that they need to do is estimate theta. Okay, so they estimate theta from the residual of the fixed effect and the pool OLS, and so they get a theta of 0.789. Again, this is an estimated theta or theta hat. Now, as you can see, the estimated coefficient of experience and the square of experience are also statistically significant. Now again, what we care is not only the significance, but the magnitude. So the magnitude of the random effect is actually not that different with the magnitude of the OLS of 0.03. But the fixed effect is quite different. Okay? And so what does it mean? Well, it means that we have to be very careful in the assumption of whether or not the unobserved heterogeneity is correlated with the experience or not. If it's correlated, then the OLS regression and the random effect regression is actually not going to be it's not going to be valid because it's going to produce a bias estimate. And in this particular case, if we assume that the experience and the unobserved heterogeneity is actually correlated, then our fixed effect estimation is going to be more desirable. Okay, so I'm just gonna go through all the regression and I'm gonna compare different estimates. Okay. Oops. Okay. So we have an estimate from OLS, fixed effect robust, random effect, and random effect robust. So as you can see here is that the OLS and the random effect are very, very similar. And again, the OLS and the random effect estimation assumes that there is no correlation between the unobserved heterogeneity and the explanatory variable. But if you want to assume that there is correlation, then the fixed effect model is going to be more appropriate. Okay, so again, I just want to provide you with a knowledge on Hausman test. And so this is just a very straightforward Hausman test. And so this is the p-value and it's 0.000, and this means that you reject the null hypothesis. And if you reject the null hypothesis, then it means that there is a systematic difference in the coefficients. And in this particular case, do you choose fixed effect or random effects? Well, it really depends on the assumption. For me, I personally choose the fixed effect estimation. Why? Because there could be variables that we do not observe, this unobserved heterogeneity, that at the same time affect experience. So it's basically correlated, and so the random effect or the OLS are not going to be valid in the sense that they're not going to produce a consistent estimate. Okay. However, again, there is a very big issue in using the Hausman test because of the assumption, assumption that there is no serial correlation. But we knew that there is serial correlation, and so what we can do is actually use the robust Hausman instead of just the Hausman. And here I'm going to use 200 repetitions and cluster. Okay, and so Stata is going to do bootstrap Stata error, and then it's going to provide us with the results in several seconds. Okay, so the result is out. Again, the robust Hausman test tells you that the null hypothesis is rejected, and so there is a systematic difference in coefficients. Again, which one should we choose, the fixed effect or the random effect? It really has to go back to the assumption on whether or not the covariance between the unobserved heterogeneity is correlated or not with the explanatory variable of interest. In this case, is experience and the experience square. Okay. All right. Thank you for having me with you in this panel data analysis. I'll see you in other occasions. Thank you.